So let me start with the definition of identity, existence of identity in a binary system or algebraic structure. That is, uh, suppose you have an algebraic system x dot, okay, and small e belongs to x, be an element, okay. Then this small e, then small e is said to be a left identity said to be a left identity okay. Monoid has already been completed. Monoid, definition of monoid. Okay, then fine. Okay, just recap this definition. Okay, so E is said to be a left identity in x dot or a right identity in x dot or an identity in x dot if, so for the left identity case it will satisfy this property if x dot e, sorry, uh, uh, it is e dot x, sorry, equal to x for all x belongs to x, or for the right identity case it will satisfy x dot e equals to x for all x belongs to x, or for the identity case it must satisfy that e is both a left identity and a right identity. That is, so this E must satisfy both the condition, right? That is E dot x equals to x dot x. So in this way you can frame the definition of an identity in an algebraic system. And okay, so an algebraic system x dot is defined to be a monoid if it is a semigroup with an identity E belongs to X. So a semigroup with an identity is defined to be a monoid. Okay, fine. So for example, you will have, so this can be uh, treated as an exercise that you need to check. So so you need to check amongst the examples given earlier So you need to check among the examples given earlier which systems are monoid. Okay, so this is your exercise. So as an example, you can always have that this is going to be a monoid. It is a monoid as it has identity and it satisfies the associativity. So for that reason, Z plus is a monoid, right? Similarly, Z dot, this is also a monoid as dot satisfies associativity in Z and 1 is the identity, as 0 is the identity, right? And here 1 is the identity, right? Okay. Now if you move on to the definition of the power set of any non-empty set X, then I have defined 4 operations on power set of X. And amongst these 4 operations, you will definitely have that if you consider the union, the operation union over power set of X, then you will see that this union is a monoid as it possesses the identity which is, what is identity? Can anyone guess?
It's a null set.
Yes, yes. So 5 as if you just execute this operation on any set, A union phi is going to be A and it is phi union A. Now for the intersection case, this is also a monoid as it has the identity. Which one? Which will be the identity for the intersection case? The whole set X as X as if you execute this operation intersection over any set A subset of X, then it will definitely give you this A. So therefore, X will be the identity. Okay, fine. Okay, okay. And also, uh, also, if we consider the system Zn plus, then it is also a monoid as which will be the identity for this operation over Zn as 0 class. Just if you add 0 class with any class, then it will give you the class again. And also if you do the addition from right, then you will get the same thing. Okay, So this is a monoid. Also, if you consider the multiplication operation over Zn, then you will find that 1 plus will be the identity. So again, it has identity, and for that reason, Zn dot will also be a monoid. Okay, fine. Now, note that, note, suppose we consider an algebraic system x dot having an identity. Okay, suppose it is E belongs to X. Suppose you consider an algebraic system X dot having an identity E, then you can conclude that, so it should be observed that this identity is unique. Without having the associativity in X. You don't need to have associativity for this uniqueness of identity, right? Why? Because suppose because if E1, E2 be two identities in X dot, okay, then just applying the equations they satisfy, that is X dot U1 equal to U1 dot X equals to X and equals to E2 dot X, X dot E2, which will imply that E1 equals to, now what you can write, just put E1 here, then you will have E2 dot E1, right? And now you consider the equation, this one. So then putting E2 here, then E2 dot E1 will going to be E2, right? So hence the existence of identity in an algebraic system is certainly unique. You do not need to consider impose associativity on the algebraic system. Just consider any algebraic system, and if it has an identity, then this identity must be unique. Okay. So in a monoid, in particular in a monoid, the existence of identity is unique. Okay. An exercise can be recorded here. Give an example of a semigroup which is not a monoid. Okay. An example of a semigroup which is not a monoid. Okay, just give me 1 minute. Yeah, fine. Okay. Okay. So yes, so you can just put a remark here that uh, that a binary system, an algebraic system can have at most one identity. Okay, fine. So now we move to the definition of another important aspect in an algebraic system, and we do feel that there are systems that I have already considered in the first lecture. So they have some elements for each element, that is, given any element, you have one element, and if you execute the operation in between them, then you will see that it will give some particular identity. It will give the identity. Okay, that is, for example, if z plus is considered, then we know that 0 is the identity, 0 is the identity, and so we see that for any integer, suppose you consider any integer a belongs to z, then you know that this equation has a solution, right? This equation has a solution, and this solution, which is denoted by minus a, right? That is, if you consider 2, then for this 2 you will have minus 2, because 2 plus minus 2 will be 0. So has a solution which is denoted by a. So this minus a will be called an inverse of this element a. Okay. Fine. Okay. Now, if you consider multiplication instead of addition over z, then what will happen? Suppose you have z dot, then what will happen? Then you cannot say that for any integer a belongs to z, there exists x belongs to z such that a dot x is going to be 1. Right? For any a, there does not any x belongs to z, satisfying that a dot x is 1. Right? Except a is 1 or minus 1. Fine. But in that case, you will see that for every integer a, it will have 1 minus a. So this property holds for every a belongs to z. But the same thing will not going to be happen in this case. Right? So these two examples shows you that the property which the first one enjoys will not be enjoyed by z dot. So this property will be an important thing to study algebraic systems, and these properties are called existence of inverse in an algebraic system where you can talk of identity. Okay, so let us consider. So formally speaking, so you can define this as follows. Suppose we consider uh, a monoid. Okay, fine. X dot, right? With the identity A. Since it is a monoid, it has a unique identity E. Then an element small a belongs to X is called sorry, 1 minute, is said to have a left inverse. Suppose you can write it as BL, left inverse, or a right inverse, BR, or an inverse B, satisfying if for the first case, that is for the left inverse case, it will satisfy that BL dot A equal to E, or for the right inverse case, A dot BR equal to E, and in the inverse case, it will satisfy both, that is BL dot A equal to E, A dot BR. Okay, that is, an element is said to have an inverse if it has a left inverse and a right inverse. Okay. Okay. Now note that if in a monoid x dot an element A belongs to X has an inverse. Right? 1 minute. I have considered it. Okay, fine. Sorry. So for the inverse case, it is B. Yes. Okay, fine. Yeah. So if in a monoid X dot an element uh, has okay a right inverse, suppose it is BR, and a left inverse BL, both. Suppose A has a right inverse and a left inverse, both. Then what will happen? Then by the definition of right inverse, you can write this as the equation as A dot BR equal to E. And by the definition of left inverse, this is BL dot A. And using these two equations, this will imply that, so suppose it is BL, then so you can write, so it is BL dot E, since E is the identity. So it is BL dot. Now you can replace E by this one, A dot BR. Now you can apply the property of associativity of dot. So this will be BL dot A dot BR, and then BL dot A will be E. So it is E dot BR, and this is going to be BR. Fine. So you see that why associativity is important here, because whenever an element has both a right inverse and a left inverse, then the left inverse coincides with the right inverse. Okay, and using the same scheme of proof, you can actually prove that, suppose uh, so in view of this proof, you can actually show that if an element A belongs to X, suppose X is a monoid, if an element A belongs to X has an inverse B, then B is unique. B is unique. Okay, I left this as an exercise to you, just using the same thing what I have did for right and left inverse case. So I did for right and left inverse case. So you can you can show that existence of inverse for an element is unique. So that means, so note, so in a monoid x dot, every element has at most one inverse, right? That is, either it doesn't have any inverse, or if it has, then that inverse is unique. Okay. Okay. So I just want to give you an exercise. Just do it. Just you consider power set of x. Power set of x. Okay. And consider the symmetric difference operation. Consider the symmetric difference operation. This is an algebraic system, as we have seen earlier. Okay. Now you need to find out, just do it now, what will be the identity, and if A belongs to power set of x, whether it does have an inverse. So just check. I would like to give you 3 minutes. So did you find out? Hello?
So the identity element will be phi and there is no inverse, I think.
Okay, identity is phi. Yes, it is correct. Yes.
But the inverse part, I can't find it.
Okay. suppose suppose you have suppose you consider one set. Okay. Yeah. Then just take this one, a symmetric difference a, then it will be a minus a union a minus a, right? So it is phi, right? So this implies a is the inverse of itself. So a is the inverse of itself, right? Okay. Now I want to give you another exercise. You will find it is going to be interesting. Suppose let x be a set and 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 let x to the power x be the set of all maps from x into itself. Okay, just consider the set of all mappings from x into itself. Then with respect to then the composition of map, we have already studied composition of mappings, right? Compose. Then the composition of mapping is a binary operation. Okay, as binary operation, that is composition of mapping means that is if f x to x be a map, g x to x be a map, then you consider the composition, that is f compose g, or you can consider also g compose f by the rule f compose gx is f of gx and g compose fx is g of fx, right? For all x belongs to capital X. And this composition is a binary operation. So therefore, x to the power x, so therefore x to the power x with respect to compose is an algebraic system, right? And also it is known to you that composition of mappings is associative, right? So as composition is associative, so x to the power x compose is a semigroup, right? Now you need to check that whether it is a monoid or not. That is, you need to find out an identity for this algebraic system. Now what will be the identity? Now you know that for any set x, there is a map from x to itself. What is that? That is the identity map. So identity map of x from x to x is the required identity in this is the identity in this algebraic system. Right? Just using the definition of identity map. So this algebraic system is a monoid. So once you see that it is a monoid, so you are trying to check whether it has left inverse, right inverse, or an inverse for any element, right? Now, uh, suppose f belongs to x to the power x, okay? Be any map from x to itself, okay? Then can you say that this f has a left inverse, or can you say that this f has a right inverse, or can you say that this f has an inverse? But you have already studied in your previous semester that if we consider a map f from x to itself, then then it has an inverse, it is invertible if and only if it is both 1 1 and on 2, right? In particular, if f is 1 1, then it will have left inverse, or if it is on 2, then it has a right inverse, and if it satisfies the both the condition, then it has an inverse. And not only that, these are the converses are also true. That is, if f has a left inverse, then it must be 1 1. If it has a right inverse, then it must be on 2. If it has an inverse, then it must be 1 1 on 2 both. That is a bijection. Okay, so I would like to record these as follows. That is, number 1, f is 1 1. Sorry, okay, f is 1 1 if and only if f has a left inverse. Now it is your task to check, okay? So this is your home task. F is onto if and only if f has a right inverse, okay? Number 3, f is a bijection if and only if f has an inverse, right? Check. So you see that you cannot conclude that every element of this algebraic system will have an inverse. It depends on the character of the map, whether it is 1 1, whether it is on 2, or it is a bijection. If it is a bijection, then it will, you can definitely conclude that yes, it has an inverse. If it is a 1 1 map, then you can say that it has a left inverse. If it is 1 2, then you can say that it has a right inverse. Okay? Okay, fine. So if a map which is not 1 1 and on 2, so it doesn't have an inverse. Okay? Okay, fine. Okay. Okay. So now the examples that we have already observed, in some examples, that is, for example, z plus, for example, power set of x with respect to symmetric difference. So in these cases, you see that it is a monoid, and every element of that algebraic system has an inverse. So this algebraic system is of greater importance in group theory, okay, in algebra. So these algebraic systems are named as a group. Okay. So definition of a group can be framed as, so a monoid x dot is defined to be a group if every element of x dot must have an inverse. And you have already proved that if it has an inverse, then it must be unique. Okay, must have an inverse. Okay, so in a group, x dot uh, we denote the inverse of an element small a belongs to x as a to the power minus 1. Okay, that is a dot a inverse dot a equals to identity, the identity of x dot. Okay, so one can define a group as, so a set. So if we if we are looking these elaborately, then one can define a group as follows. So a set x uh, a set x is said to form a group with respect to a binary operation. With respect to a binary operation dot, if it satisfies the following. What are those? The first one is number 1, that is, for every pair of elements a dot b belongs to x. Although we do not need to write this, but in some uh, sense, there are books who have just written down this as a uh, as a condition, and this is called the closure property. Although you do not need to write down this inevitably. Okay. Okay. Number 2 is for every A, B, C belongs to X, it satisfies the associativity, right? It is a semi-group. Associativity. Okay. Number 3, there exists an element E belongs to X such that E dot X, X dot E equal to A for all A belongs to X, and it is called the existence of identity. Yeah. And number 4, for every A belongs to X, there exists an element B belongs to X such that A dot B equal to B dot A equal to E, and it is called the existence of inverse, right? Okay. And we denote this B as A inverse, which is unique, right? So in this way, so you can define a group like that. Okay. So if you want to recap, then you can say that in an algebraic system X or a set X is said to form a group, is said to form a semi group if it satisfies 1 and 2. It is a monoid if it satisfies 1, 2, and 3, and it forms a group if it satisfies 1, 2, 3, and 4. Okay, fine. For example, so already we have seen that Z plus is a group. You can check that Q plus is a group. You can check that R plus is a group. C plus is a group. Are groups, right? But Z dot is not a group, right? Why? Because 2 doesn't have an inverse, 3 doesn't have an inverse, 4 doesn't have an inverse, and so on, right? Okay, so it is not a group, but uh, Q minus 0 dot is a group. Q dot is also not a group because 0 does not have an inverse with respect to multiplication. But except 0, all other elements do have an inverse. But 0 does not have an inverse with respect to dot in rationals. So if you take out this 0 from Q, then you will see that yes, Q minus 0 will form a group with respect to multiplication. And in a similar way, you can say that R minus 0 dot is a group, C minus 0 dot is a group. Okay? Okay, fine. And you have also seen that for any set x or set of x with respect to this is a group, right? You can check the same thing for other operations defined on a power set, right? Okay. Number 4, Zn plus forms a group. Why? We have already seen that Zn plus forms a monoid. Now we need to check that every element of Zn must possess an inverse with respect to addition modulo n. So let A class belongs to Zn. You need to check whether A class does have an inverse with respect to addition. So what would be your guess? That is, so you need to find out a B class belongs to Zn such that A class plus B class will going to be 0 class, and B class plus A class is going to be 0 class. So that means A plus B class 0 class, B plus A class 0 class, right? Uh, that is, yeah, sorry. that is so to satisfy these equations, so this will hold if if n divides A plus B. That is, if A plus B equal to some nq is a multiple of n. That is, if B is uh, yes, nq minus A, right? Now you can write down this nq minus A as nq minus n plus n minus A. So it is nq minus 1 plus n minus A. So that means it is nq dashed plus n minus A. So what is B? So B is, its class will be n minus A class, right? Since B minus n minus A will be a multiple of n, this one. So B class is n minus A class. So what would be your inverse for the class A? N minus A. That is, if you consider one A class, then you can definitely have the inverse as n minus A class. That is, suppose you are in Z10 and you consider 3 class, then the inverse of 3 class with respect to addition is 10 minus 3 class, that is 7 class. Okay. So every element in Z plus, so every element in Zn must have an inverse. With respect to plus. Yes. Okay. So Zn plus forms a group. Right? Now, if we move on to the operation dot, now if we consider the operation dot, that is multiplication modulo n. Modulo n, then what will happen? Now it is clear to you that with respect to multiplication, Zn dot is a monoid. So it is obvious that Zn dot is a monoid, right? Okay. Then does it form a group? That is every element in Zn, does they have an inverse with respect to multiplication? Suppose an element A class belongs to Zn, A class belongs to Zn has an inverse with respect to dot. Okay, say B class, that is A class dot B class is one class, right? That means AB class equal to one class. That is n divides uh, n divides 1 minus AB, right? That means 1 minus AB is a multiple of n for some q belongs to Z. So AB plus nq is equal to 1. So what does this speak? So it speaks of that GCD of A comma n is 1. That is A is relatively prime to n, right? Relatively prime to n. Just write it here. Relatively prime to n. So you see that if an element in Zn has an inverse, then it must satisfy one particular important property, that is this integer a is relatively prime to this n. Now we would like to check the converse one. Suppose GCD of a comma n is 1, then there exists x y belongs to z such that ax plus ny is 1, just using the property of two relatively prime integers, right? That is, if GCD of a comma n is 1, then you must have two integers x and y which will satisfy ax plus ny is 1, right? Using Euclidean algorithm. And this equation implies that 1 minus ax is ny. That means n divides 1 minus ax, and that means ax class is 1 class. That is, a class dot x class is 1 class, right? And similarly, if you can check, then you can check that x class dot a class is 1 class again, right? So this implies a class has an inverse. X class in Zn with respect to dot. So thus, you can conclude that thus in Zn dot, an element A class has an inverse if and only if GCD of a comma n is 1. So you have completely characterized the inverses, the elements that have inverses in Zn dot. So these are some important elements Zn has. That is, these elements have some special property, that is, the GCD of a comma n must be 1. Right? Fine. So thus, so hence, in general, Zn dot doesn't form a group. Now one may tempted, so one may be tempted to check if we just take out 0 from Zn, does it form a group? Now suppose we consider Zn minus 0, 0 class. And the question is, does it form a group with respect to dot? For example, suppose let us look at the example. So let us look at Z8 minus 0, comma dot. It is a monoid. There is no doubt that it is a monoid. But you need to check whether it does form a group. Okay? No, I'm sorry. It doesn't form a monoid. It actually doesn't form a groupoid. Why? Yeah. Now, it doesn't form an algebraic system. Why? Because this dot will not be a binary operation over Z8 minus 0 as 2 class dot 4 class. What will be this product? This product will be 8 class. Now what is 8 class? 8 class is 0 class, since 8 divides 8. So 8 class is 0 class. So that means this 0 is not here. So this operation will no longer be a binary operation over Z8 minus 0. Okay? Yeah. So what is the indication? It shows that since 8 is not a prime, it is a composite. It is a product of two integers which are less than 8. Right? You note that 8 is a composite. So in general, if n is a composite, that is, suppose it can be represented as a product of two integers p and q. Yes, n 1 less than q less than n. Product of two integers p and q. Yeah. Okay. N equal to pq. Then n class is pq class. Now what is n class? Since n divides itself, so n class is 0. So p class dot q class will be 0 class. But that 0 class will not be in Zn minus 0 class. So this implies dot is not a binary operation on Zn minus 0 class. Okay. So since n is a composite, so you can definitely conclude that Zn minus 0 class will not form a group with respect to dot. Right? Okay. Now suppose Zn minus 0 class dot forms a group. Then what will happen? Then you can write this, the fact that every element A class in Zn minus 0 class has an inverse. Now you have already proved that an element in Zn has an inverse if and only if GCD of A comma n is 1. Yeah. So that means okay. So that means GCD of A comma n is 1 for all A class belongs to Zn minus 0 class, right? That is, this A is prime to n for all A class belongs to Zn minus 0 class. Okay. So suppose if possible let n be a composite, then what will happen? Suppose n be a composite, then we can write n as n equal to pq, 1 less than p less than n, 1 less than q less than n, right? Now, now uh, so yes, okay, okay. So GCD of p comma n is 1 from this one. So that means there exists x, y belongs to z such that px plus ny equals to 1. Okay. Okay. So that means then what will happen? Then uh, pqx plus nqy equal to q, just multiplying q on both sides. So this pq is n, so it is nx plus nqy equal to q. That means n divides this n x plus nqy, which is q. That is n divides q. But does it happen? No. Why? As q is less than q, less than n. So a contradiction. Right? Similarly, if you consider GCD of q comma n is 1, then you will see that n divides p, which is again a contradiction. Right? So thus, what we have assumed that n be a composite, in that case, so it will raise to a contradiction. So our assumption was wrong. Was wrong. And so, and this implies that n will not be a composite, n must be a prime. So thus, so hence we can say that Zn minus 0 class dot will form a group if and only if n is a prime. Okay? Okay. So I should end here today.